Good morning. For January 27th, this is a take two on what I started off with early this morning. I had a crash in the recording system, so I'm just doing a short little segment to fill in what got missing, especially since there was one person who had to miss class for a surgery. So I'm just explaining a little bit about what led into, and then we'll switch over to the video that was captured on the second go around. So we're getting started again. We're finishing up what we had in chapter 1 of the notes, the intro, and I will later in this lecture talk about homework. It turns out in the end of the class, and it will be refreshed on the website here. Actually, I'll just refresh it right now since I've already pushed this up. That in class today I decided to give you until next Tuesday to turn in the homework. This paragraph that's written here at the very top is now history because I pushed it over into Slack along with a screenshot about you turning in problem 5 and problem 6 by the end of the day on Tuesday. And you can read more about this later on your own. If you're not watching the video, just jump over to the website and also look on Slack. At any rate, we started off with returning back to the block diagram of communication systems, and I made a comment about the fact that really from the standpoint of what a communications engineer works on, they're working primarily on transmitters and receivers. And we come up with a waveform design of what we want to transmit, or we're supporting a legacy standard, and then the receiver has to get implemented to receive that waveform, whether it be an analog or digital. Today it's far more common to be digital. And as I think I pointed out sometime this morning, I had thought about bringing in a really simple example of a transmitter, at least, that all of us carry around with us, and that is our key fob for our car. We also have a garage door opener typically, and those transmitters at one time were very simple, 100% analog, and now they've become far more sophisticated with sending rolling codes and things that go to the receiver in your garage or in your car for opening the doors. So even that's gotten more sophisticated, but I was trying to think of a very simple radio device that we carry around, and about the simplest one I was coming up with in my mind is the key fob, and that's really not all that simple anymore either. At any rate, we talked, and this is what got clipped off in the video, about channel types. So radio frequency or RF communication is by far the most commonplace. There's other forms that are talked about further down the page, and we'll get to shortly, but this picture, which comes from the book, is just showing you that in RF communications we have various modes, and probably the most common is point-to-point communications on the ground, which might be ground wave if it's low frequency, follows the curvature of the earth, or more typically it's point-to-point or line of sight, or in the case of the example here, an aircraft would be line of sight. We would also try to do line of sight with cell phones to the cell tower, but usually there's obstacles in the way and there's multipaths, so there's multiple paths that we'll get between our transmitter or the cell site's transmitter and our receiver and make it more of a multipath type channel, which is a little bit more complicated. Another type that's very common is passing through the ionosphere and going up to do satellite communications. Very common these days to be, especially in Colorado Springs with all the technology companies that support Air Force missions and things with satellite communications. We, of course, have commercial satellites that we talk to. So those are approximately line of sight, but there is factors such as I mentioned last week, there's Doppler, and there's noise of various types that are involved in that channel as well, but it's not a multipath channel like we have on the ground. And then we have in between, we have the ionosphere and the particles in the ionosphere, which When it lowers slightly and gets more dense at night, we have it forming like a screen. So we have medium and low frequency signals will not penetrate through the ionosphere, and they will reflect off of the ionosphere and can get what's called skip wave propagation in this figure, where it bounces from one side of the U.S. to the other. As a matter of fact, AM radio broadcasting has had to deal with this, and it's all in its entire history, and that is that AM stations are what are called clear channel stations in various parts of the country, where they get to keep their power level up all through the evening when the ionosphere reflections are happening, and that ensures them that they don't compete with other local channels. The local stations have to dial down their power so that these clear channel stations can occupy the 100+ AM radio broadcast slots that are out there for the entire country. We reuse all those frequencies from community or locale to locale. So interesting there, the way that all comes together. So there's more to be said, and I'm going to stop this repeat section, and we'll jump into a slide when we see the next screen come up. It'll be starting right here with more discussion. So bye for now. I don't know whether it actually stopped or not. Hopefully it's going to keep going here. It says I'm recording. So microwave, RF frequencies all up and down are what are used for most all communications, but not everything. These bullets are pretty much what I described to you. This is some charts that are in the book, just showing you the history and also what activity is at. I'll later show a chart that is maintained by NTIA, I think, or the FCC. It's just a really dense spectral chart that shows you with color bands what are all the allocations, starting way down low, like at 3 kilohertz, 30 kilohertz, all the way up to terahertz, which is actually going to be optical. Now, I think I told you that when I worked at White's, when I worked on my first, for my first company was Motorola Government Electronics, and I remember the name now. It's General Dynamics down in Scottsdale, Arizona. That's where I was working. And General Dynamics is also in Colorado Springs, I believe, an aerospace contractor. At any rate, I was up in my system operated in the green and infrared, so it's way up at the bottom of this chart, the highest frequencies. But most of the time, we're operating down lower because of propagation conditions and so forth. Laser light propagates in a very straight line. It doesn't diffract. It doesn't spread. It offers great security, for one thing. If you can broadcast a very narrow beam, you're basically pointing it at just one person and nobody can get in the path to intercept it, right? Now they could get in the path and block it, which would be not such a good thing, but so I worked on LaserCom, and that was one of the intentions. It tested at the White Sands Missile Range, as I said last week, just because they wanted to test it over the desert for initial tests, and then they did an aircraft flying out of Holloman Air Force Base to a dome in the missile range, the green laser light in one direction and the infrared in the other. I'm now getting kind of into the soft side of things. What was cool about it, when I was at the range at night and the laser was transmitting down 1 gigabit per second in free space, it was a green laser, so it was a green kind of eerie glow that was coming down onto this dome that was tracking it. The infrared was a beacon laser to help align from the transmit side, and it was pulsing with a very large power, such that when it was running, we had to wear goggles, our infrared filter goggles, to make sure we didn't get eye damage. It was kind of a
crazy thing, but there was a light flashing inside the building, and the infrared was on at that point. And my experience with that was I read about what happens with infrared of a high power. It'll just melt your eye very, very quickly. It'll destroy your vision. You don't want to get too much optical. So whenever I see laser pointers around, I think about how laser pointers actually do have warnings on them if you haven't ever had one to play with. Maybe you have one for your cat or your dog. It makes me think about laser safety, though. So what are some of the other bands as we work our way up? When I was going to school at Michigan Tech in Upper Michigan, they were installing a grid called the Sanguine Seafarer Project, which was in the forests in the Upper Peninsula of Michigan. Michigan Tech is in the Upper Peninsula of Upper Michigan, which is called the Keweenaw, which is sticking out into Lake Superior, if you're just not familiar with that. It's a very isolated place. Remember we talked about copper mining last time. But they were putting this grid in, and it was a grid very low frequency in the kilohertz region that could transmit basically through the Earth itself. And it was designed for communicating to submarines and things that are underwater without them having to come near to the surface. And I don't know if that's still being used or not. It was not a very high bandwidth because it's at such a low frequency, so the data would not transmit very rapidly. But in a time of, war and so on, what do we need to communicate rapidly? If it's a matter of launching a missile, it's just saying, hey, this is what we want you to do it now. I mean, how much bandwidth does it take to send that sort of a message, even encrypted and so on? We come up into the kilohertz above that, and the next band up, 30 to 300 kilohertz, so that's 30 kilohertz, which is above our hearing. That's like ultrasound, but up to 3 megahertz there. 3 megahertz is the next band up. Would take us up through broadcast AM radio, which goes up to about around 1200. So I'm thinking of commercial AM radio, other things that were eventually created. Most every one of these systems that we see up here has probably got other newer generation things, but beacons and things. I used to sail on the Great Lakes a lot growing up, crossing Lake Michigan into Lake Huron. And remember I told you my father did amateur radio, so everything that we did was communications. If we had radio direction finder on the sailboat or something, we could look for navigation aids that were broadcasting code words and things. We'd look it up in a book called The Light List, and radio list that would say there's a marker out here that's marking a shoal and it's broadcasting this code. It was usually Morse code pattern or something. Sounds really crude, but ships have to navigate, right? So radio's been used for that too. Lower frequencies though, AM broadcasts, amateur radio, pretty much what's called high frequency is in this band, 3 to 30 megahertz. But it's been used for other things too, not just amateur radio, which is people wanting to play around with radio signals. It's been used for other navigation aids, aircraft at one time, and ship-to-ship communications and other such things. Nowadays, your mind probably says, this seems so old-fashioned. Well, you're right. Satellites are up there and people can do satellite communications very readily. But we still have these legacy systems around, and I'm pretty sure they're still used. I mean, they were used when I was growing up, which is, I'm not a young person, but they were used all the time. You could listen to the Coast Guard, and you could radio to the Coast Guard wherever you were, because there were generally stations and light stations and things that were manned by Coast Guard people, and you could raise somebody to get emergency rescue or something. So coming up higher, we used to have VHF television, channels. Those are gone now. Those went away when we came along with a totally new standard quite a few years back now, as it stands, HDTV. So we annihilated and did away with some frequency bands, and they've been repurposed since then. FM radio is still present, air-to-air communications and aircraft to tower. We can still do that. He has listed in here taxi cab. I mean, way back in time, taxis could be dispatched radio-wise. How do they do it now? If you go for a taxi ride, they don't have a point-to-point radio. They generally just use their cell phone, right? But as these infrastructures came into being, the old legacy stuff either was repurposed or is just sitting, not used very much. I'm not really familiar, but there were dedicated two-way radio channels certainly for police, and they still have that. It used to be that you could intercept and listen to the police talking to them, and fire trucks and ambulances and all that stuff. Most of those are now what are called trunked radio networks, and the trunked radio networks generally have encryption on them, and they're digital at that. So intercepting and hearing them was not something you could do like you used to be able to do. Has anybody ever done that? Listen to a scanner that picks up signals like this? It's kind of fun. My father would do it all the time, and he would know if there was a bad accident somewhere or if something bad was going on. And I shouldn't tell you this, but you could listen to baby monitors. All kinds of things you could listen to. So, if you lived in an apartment building like I did, you'd listen to people making phone calls. I mean, you guys should be able to believe this, right? You tell somebody that's not an engineer that, oh, I could be eavesdropped on, they're probably shocked. Like, I would have never imagined that. Well, it's just not. We didn't grow up having all these security measures, so. UHF television is part of what became HDTV, so there is still this higher band of frequencies. And then we get up even higher, and we're just into other navigation aids that are at microwave frequencies, surveillance radars, and of course SATCOM, so on and so forth, weather radar, landing systems. And then, like I said, I was saying I was in optical comm, so that's way up here at the top. This is an interesting study unto itself, because this is something that Dr. Zemer believed was going to happen when he wrote the most recent edition of the book. He thought that we were going to give up this nomenclature here, and let's make that a different color. And we were going to end up with more or less this nomenclature, these letters of the alphabet. It never happened, as far as I can tell. All the work that I've done over the last, say, 20 years has been still using these designations like S-band, C-band, L-band. L-band, for example, is where GPS signals lie, that we pick up our GPS satellites. S-band, the project I was just working on a year ago and just finished in October, was an S-band communications link, originally a technology developed for the space shuttle, but it's now repurposed over and over again. So the space radio I was working on was implementing a TDRSS, tracking data and relay satellite system. Has anybody ever heard of that? TDRSS. It has S-band and K-band, or KU band, I guess, or X-band. So the radios I was working on were S and X-band for this Blue Origin project that I was on, the Blue Moon project. I was working in the S-band radio, and others were in the X-band radio. So most of you, if you have done internships or you're going to go work somewhere, you're going to see probably you work on a radio length that's It'll say it's an S band something or an X band or K or KU band, something like that. So this just refers to some of the other specific designations. This was what I was talking about before, the 30 kilohertz, the Sanguine Seafarer project. And by the way, we're engineers in the radio space. People in the biology and other, backgrounds will say we're worried about RF, and RF, some people are very sensitive. Mark, who taught this class last year, Mark Frank, who passed away in September, his wife has a radiation sensitivity. She can't be around any radio waves. She has to not have Wi-Fi, a cell phone, or anything because she gets sick or something. He explained it to me, but does anybody know anybody that has a radio frequency sensitivity such that it really is unpleasant for them? I mean, I'm surrounded by devices like my Apple Watch. There's Bluetooth and everything running around. But some people are highly worried about that.
I mean, it's hysterical.
You think so?
There's radio waves everywhere.
It's a biology thing, and there are forums, there's things on the internet. Obviously, you can find a whole discussion on that. I don't think it's what's called non-ionizing radiation, and we can tolerate it, most everybody. And some people, I worked for a company, Paracle Communications, that did outdoor propagation interference, and if they had a homeowner that was near a cell tower or something, they would get hired to go in and take some measurements right inside the house and then talk to the homeowner. And the guy that ran the company worked on both sides. He would work for like police department, fire department in Denver, trying to make sure their radio networks were working well for dispatching and so on. And then occasionally he would do work for, individuals that were trying to say, you set up this tower close to my house and it's making me sick, and so on and so forth. And that's what you're talking about, right?
Hysterical means more like it's all in your head. So
yeah, I know. But I didn't get involved with it. I just knew that he was working on it, and just be aware of that fact, though. You may occasionally run into somebody. I've run into almost nobody, but I do know, like I said, Mark Frank's wife has it, and I've known other people that it bothers them. So I'm not the psychology person. Take psychology, though. I did take psychology as one of my social humanistic electives because I wanted to learn about that stuff to some extent. So this is a very popular band, though. And there's ISM bands that cover various frequencies up and down. The most familiar ISM band, probably to all of us in this room, would be the 2.4 gigahertz ISM band. That's what a lot of the devices that I'm using right now. Bluetooth is in there. The lowest frequency Wi-Fi is in there. But there's also microwave ovens in there.
Heaters and welders, why do they need radio?
It might be harmonics and overtones. I know if you go up to Washington State, they have a lot of timber up there, and they make a lot of plywood. I know in making plywood, where you're fusing together layers of wood with glue and heating, they use induction heating, and they radiate a lot of RF interference off of those devices. Has anybody else ever heard about that? I mean, you know there's a lot of wood products made in Washington State, though, so I know that is a source of radiation, and you wouldn't want to be next to somebody like that because it's probably going to wipe out your Wi-Fi or something. I mean, in my household, for example, my microwave oven, I brought home the Field Fox one day, years ago now, and Brought home the Field Fox, put an antenna on it, brought it close to my microwave oven. Yeah, it radiates a fair amount of power. It's not a dangerous amount, but it interferes with my Wi-Fi router at times. It definitely stresses it out. And I look at it as sort of a frustration thing. I mean, if you're in Wi-Fi, what do most wireless Wi-Fi routers do today? They do something called, what was called cognitive radio many years ago now. But cognitive radio means you have the ability to think in your transceiver, what frequency do I want to be on? And Wi-Fi has, in the 2.4 gigahertz band, we'll look at this later, it's got so many assignments that are open to you. And you can set your router up to just camp on one. But chances are you want to use it in the cognitive radio mode because your neighbors all around you have something. And they maybe already are camping on some other frequency, or their router has found that frequency. So your router just has to sit there and listen and decide, where can I put my household, this instance of a wireless router such that I can get a clear channel without being interfered by another router. Has anybody ever experienced issues like that? I mean, I've had students before, people I work with, that say, yeah, my neighbor is on this frequency, I want to be on this frequency. We were getting low throughputs because we're clashing a lot, so we manually set our routers to be on a particular Wi-Fi channel. I mean, electrical engineers, communications people are the ones that are more apt to want to do that, just because they know how to coexist. There's the different cell phone bands. We have cellular, 900 megahertz. The other cellular bands are in 1.8 to 2 gigahertz. By the way, CDMA cellular, this was generation 2, so now this table wasn't updated, but we're in generation 5, 5G mostly these days. So how, I've been talking a lot about interference. How does this get managed? It gets managed through organizations. There's a worldwide International Telecommunications Union, ITU, and then there's radio conferences that are held worldwide. Within the United States, we have the Federal Communications Commission. So all of this is regulated. If you transmit over such and such amount of power, you have low power devices. When I talked to you about making bootleg transmitters last time, that's what I started off doing, but then I realized you can make it more powerful. I mean, it can be as simple as a wireless microphone, an FM broadcast band wireless microphone, or set above or below where you don't interfere, that you might want to, put a mic on somebody. Churches are using wireless microphone systems all the time, and my church is at a corner where there's a church across the street and another one kitty corner across another intersection, and my son is involved with audio and video processing, and I know there's interference caused by just their wireless mics are on the same channel sometimes. Aggravating, but we have to get along. And for those of you taking the lab, there's going to be a time in an experiment where you're going to be using the function generators that go up to nice RF frequencies, and you're going to be putting an antenna on them, and you're going to actually be broadcasting to your device, but then you're going to, have it purposefully set up so that you can see what it's like to interfere with somebody else in the lab space. The intent is not to cause interference outside the lab, but it's just to give you an appreciation for how you can create interference. So you can become like a small-time radio operator and transmit something through like a flex antenna that I've got on here. So a key thing here that I added in is it's on the move all the time. The FCC continues to make changes, and like I was saying, when HDTV came along, it opened up some bands which were quickly reassigned, and then some other bands were given up elsewhere, and then HDTV had a place to go, and then some other things came into play. I use Comcast in my house right now, and Comcast has wireless access points around the city, right? So if you have if you're on Comcast, you can use some hubs that they have around the community, and I think other providers have that too. So that's all sharing and such. What I did not mention, though, is that when the FCC is making allocation changes, they do have auctions. So they auction spectrum because the spectrum is a natural resource. Very, very simple. Just like we have natural resources for mining, growing crops, oil underground, and all these other things that we have. The frequency bands are truly a natural resource. If we did not share them, what would we be doing these days? We wouldn't be having our devices work very well because we'd be interfering with each other a lot. So we have to be able to do that. And you might wonder, how do our Bluetooth devices work so well? Because my Bluetooth right now is spreading around to everybody else's Bluetooth in this room. How can we overlay? Well, it uses a method called frequency hopping. So it hops from one frequency band in the ISM band to another, and your device hops as well. And the theory is that the hopping is moving around enough that you're not hitting each other that often for a given locale. That's part of the design, and that's sort of an engineering, design issue to make sure that happens. Okay, another thing that gets involved with the radio channel is absorption. So we have, besides just the free space path loss that we have in radio communication, and just to review that quickly, if you have a point source radiator, suppose this was the transmitter, or I had the other radio that I passed around last week, you can view it as a point source from electromagnetics. And so it's got 1 watt into it, and if that 1 watt of RF power produces a spherical wavefront, simple enough, right? Just thinking in terms of a spherical wavefront. So it's radiating equally in all directions. It produces so many watts per meter squared, because that's what happens when you radiate out spherically. You're going to have, think of that 1 watt as getting painted uniformly on a sphere of some radius. That will give us watts per meter squared. The antenna has an effective aperture area that represents so many meters squared, and it will capture then watts per meter squared times meters squared becomes watts again. Does that make sense? I'm just talking about units now, making sense. You'll get watts in your receiver back because it has an effective aperture area, and the transmitter is transmitting its power spread over so many meters squared, and that diverges the further and further you go away. So we'll study that at the very end of the semester when we're looking at link budgets and things, how the distance, the path loss is inverse to the distance squared. And you probably heard that before. So, but what aggravates things, especially going up into space, is there's molecules in our environment, oxygen and water vapor. So oxygen has, you can see in this chart here, 62 gigahertz, 120 gigahertz. And then water vapor has other resonant frequency points. Now most of those are above where we typically communicate. 5G and 6G wants to do things in millimeter waves, which is up there over 20 gigahertz. So they have to be cognizant of the fact that there are resonances in the medium, and that dB per kilometer will add up the more kilometers you're going, so you will see that more. Now, an advantage of this is turning this around, though. This has got certain advantages. Suppose to RF crosslinks up in space wanted to not be heard on the ground due to the antennas maybe spraying some of the radiation down onto the surface, what's an advantage of having this known fact? You can broadcast at a frequency that the water vapor and oxygen will not let pass through. Sound good?
Water vapors, clouds.
Yeah. Yep. People have thought about that. And then taking that even a little bit further, just on the ground, we have attenuation just due to rainfall. And if you study this, and I've studied it before, in the technical terminology, a raindrop is called a hydrometeor. So they say hydrometeors, drops of water. So depending upon the rainfall rate, you get higher attenuations. So light rain shower, say 10 millimeters per hour, that's the lower chart there. The upper one is heavy downpours, and these things do happen. So satellite communication links have to take into account, if it's a commercial one, let's say, the link budget has to be able to tolerate things. And if you have a really heavy downpour over a locale, it might wipe it out, just because you won't over-design a system to always have enough spare transmit power to handle a really heavy downpour, because that's just doesn't happen very often. It's a probabilistic thing, but when it does happen, it will cause what's called an outage, because the link can't support communications because of the attenuation that's temporary like that. There's guided EM wave propagation. So when we do wired communications, we're sending our waves through, say, a coax cable, a twisted pair. Twisted pair is what's very common in a wired router like what we have here in the building. I'm on the wireless side, but I know there's twisted pair from a hub that comes into this podium here, and you might use that in your house. I don't do that at all anymore. In the very beginning, that's what we had, right? In the very beginning, we had twisted pair telephone lines that we got our data over. There's magnetic recording channels. We used to use disk drives, magnetic media a lot more. We basically don't use it at all anymore. Most of us have solid state drives on our laptops, but they're still used for backups and storage things in some situations. Some of you might have Blu-ray players still at your house, but how often, all that stuff went away too. We came through it, and it's behind us now. I remember Blockbuster, for example, rent a video, but it's just gone, right? Think of these people that invested in that. Some people came out really well, and then the technology got supplanted by something new, and then it's just totally gone. Optical, I talked about free space optical that I worked in. At one time, free space optical was something that was talked about for even indoors, and we had devices. We had optical sensors on laptops at one point. The idea was there would be like a detector that's in the roof, maybe the smoke detector that you see up here might be a dome that was for infrared. And it was talked about. It never really made it to the level that I thought it would come to. Again, it has advantages because the free space optical would be very localized and wouldn't go outside to allow eavesdropping. Fiber optic, though, is definitely extremely important in worldwide communications. It handles more total bandwidth or bits per second net than any other medium does, just because there's so much available bandwidth in fiber. So to jump off and look at something I was talking about last time, because I have the Colorado Springs Utilities fiber already in place around in my neighborhood, which is just 2 miles east of here. Ting is the service provider that the city is letting make money for themselves and pay the city for the infrastructure that they would have charged us for as taxpayers on the city utilities. So Ting is pressing this theory that they're going to have a direct fiber 100% of the way between the internet service head end and your house. Whereas in my neighborhood also, we have other providers, which I was telling you about last week. I've talked to them when I'm out walking my dogs because they're always tearing up the easements in the front of all the yards. They're making a mess, actually. Or they've done things and they haven't compacted and then things settle. It's kind of a mess. But so other providers are trying to compete with them, but they're a hybrid of fiber and copper. So they're not as good because the copper won't have the same bandwidth. Copper means coax, typically. So when I first looked at this is my address right here. This was about $69, and I noticed now it's gone up by about $20. So I can have it at my house because I have a pedestal in my backyard that they bored laterally through my yard and put it in the corner. $89 a month. And I've been noticing a lot of Ting trucks in my neighborhood, so a lot of people are getting the drop from the pedestal into their house. Does anybody have it? Okay. Would you pay $89 a month?
My dad does.
Okay. Does he have Ting or something?
It's, what's it called? Stratus IQ.
Okay. There's, like I said, there's just a lot of other things out there, but the city is doing this methodically over the entire city. It is a huge project, so I thought that might seem interesting to you. There's no head end, though. Like Comcast offers all kinds of services, and they're just feeling threatened right now. I know they are because I get emails from them saying, we're going to do this, we're going to give you this. You know, they've got to make sure they don't have this thing called churn. Churn is the term that providers use to describe how they're advertising to try to draw people from one wireless provider to another. And they want to just create this churning effect where people are just constantly moving around. So Comcast is saying I'm a Diamond Plus customer because I've had service for over 10 years, and they want to give me some extra perks. I don't watch TV. My wife and my son watch TV a lot. I don't really watch much TV at all, but we do use it for the internet. So I don't know whether will change at some point in my household, but what plays in at the top level of all of the communications that we talk about in the class, but we don't really deal with it, is we have this thing called the Open Systems Interconnect Model, or OSI model, and it consists of layers. So we have various layers in the OSI model. We have the top layers, which is data-centric. We have, so application, presentation, session, those are way at the top of the stack. And if you're building a wireless device, like a Bluetooth device, to do something, you might get a software stack that allows you to, effectively represent or abstract these things into your product. And if you're doing that in a capstone design, you might do something like that too. You might just use the software stack to be able to bring that into your hardware design. You drop on down, we have transport, we have network, which is now starting to become real to me, packets. We have data link, MAC, in particular media access control. Most all of us electrical engineers were familiar with media access control. Address. You get a device and you look on the back of it or something and you see the MAC address that was assigned to it when it was manufactured. Drop to the very bottom now, and we have the physical layer, and that's really what this class is focused on. So if you wanted to be in those upper layers, you have to be over in a different domain. Still electrical engineering, computer engineers, and computer science people would be more in that layer, but we're on the physical layer. The closest I get in a daily thing, day-to-day thing maybe, is knowing a MAC address, sometimes having to put that in to configure something. Okay, low-cost software-defined radio, I mentioned that last week. This came along, this is a really old diagram, but it still applies. It came along to say that rather than having a simple device, and I thought about bringing the one out of my car that I use every day, and that's my garage door opener. That's a very relatively simple wireless device. It's a transmitter that used to be purely analog, and now it's digital with encryption and rolling codes and all kinds of other things, right? And most of you know that. Or, never mind, I do have my Toyota key fob here, so it has a very similar wireless nature to it. It's a transmitter. It has rolling codes and all the other things that had to be added. But if you are worried about it, it can be hacked too. And any and everything can be hacked. So my understanding is criminals have their means of getting hold of things to hack and break into cars electronically. I don't study on this, but I've read articles every now and then about the technology, say, in the key fobs or garage door openers. Is anybody ever else worried about that? Right? I mean, you go to the gym like I do a few times a week, and if they break into your car and your registration is in your car, they'll have your registration if your garage door opener is sitting right there. They just have to grab that, and then they can go to your house and break into your house, figuring maybe you're not home. There's all kinds of stories about things like that happening, and I've had students that have had things, they've had their backpacks stolen, for example, out of their cars, and they can't get their homework in. I mean, I heard about it, only because they didn't have the ability to get their homework turned in. But a more sophisticated radio would have the RF and IF front end, which is the analog stuff up here, but then you would go between A to D and D to A for transmit and receive, and then you have a digital front end, so you can do channelizing and sample rate conversion. I mean, I'll just, since I've got this here again, that's exactly what this does. So this thing is transmitter and receiver all in one USB dongle. And then it has the processing. It maybe doesn't have all of these things, but it has FPGA, DSP, maybe ARM core in a FPGA that's a Zinc, the Zinc chip that Xilinx, which is now part of, see what's the company that bought them. I get ads and training and stuff because project I just finished on in October was all FPGA based, but it was on a very old FPGA, so it didn't have the ARM cores in it. But the company I worked at before, when I left here originally, was doing the Zinc chip for software-defined radio stuff. It was for CubeSats.
AMD bought.
Yeah, AMD, that's what I'm thinking of. Yeah, AMD, which is huge now. They're making lots of money right now. What are they making all their money on? My understanding. Does anybody know? AI, right? So they make the big server centers and all that stuff. I have a son who's an architect. He works in Denver, but finding places to put the AI server farms is now a big logistics thing. You got to have water to cool everything. You have to have the grid to supply the power. I don't know. It's making me a little bit nervous. We're going to put so much power into our AI processing that we're not going to be able to do anything else except do the artificial intelligence searches and stuff. I don't know. You guys are going to be seeing this throughout your career, though. I don't know what it's going to bring, but it's definitely a a factor.
What's
At
IF?
intermediate frequency. So what will happen in our receivers, like in the lab, will come in at a RF frequency, and then it will down convert to an intermediate frequency, like broadcasting used to use 10.7 megahertz. It might be 70 megahertz in a satellite receiver, something along those lines. And then you process from there. So one of the things we'll study a lot of up in Chapter 3, we'll get into it, will be moving signals around by frequency shifting them. So we're going to start learning that in our review here in Chapter 2. So what I have in the lab is a $20 SDR. The one that I have on my USB-C that I'm going to fire up here in a moment is the next about 2 generations beyond the $20 one. So this one was $30 or so. It's got a much more sensitive and stable oscillators inside of it, and it has a form factor that's a little bit more conducive. The original RTL SDR was a hacked version of a device that was used in Europe for TV. So they took the chipset, and people figured out how to use the chipset that was in this device. And I think I have a picture of it in here, maybe not. It's in the lab, probably. They figured out how to hack this device in such a way that they could make a low-cost receiver out of it, flexible, write drivers for it, and so on and so forth. So repurpose it from what it was originally intended for as a TV receiver. We didn't do that in the United States, but in Europe they were doing this. So this is what the chipset looks like in the original RTL SDR. It outputs in phase and quadrature or real and imaginary samples at 8 bits per sample, which sounds like what can you do with only 8 bits per sample, but it's an RF signal. So it starts as an RF signal, and it's at a very high sampling rate, so you can get a lot of bits of resolution effectively off of that, and you can do your demodulator. So this is a block diagram I created, and this kind of shows you what my abstraction idea of the software-defined radio is. You come in through a low-noise amplifier. That's what LNA is. You have the ability through the USB interface here to control analog settings of that LNA. So you're actually pushing signal settings into an analog component in the front end. You then have a multiplier, and I'm abstracting that to say it's just a complex exponential. So if you remember this, and we're going to be going through this very soon, that's complex frequency translation in the Fourier domain. When you multiply by e to the minus j 2 pi fc being a carrier frequency in t. So that is a theorem in Fourier transform theory, which is huge in radio. So we can move a signal around. We can move it up and down in frequency and make it pass through DC, I mean a low-pass filter centered on 0 hertz, apply some more gain. VGA is variable gain amplifier, could be an automatic gain control setting, and there's different modes. And then finally you quantize things down to 8 bits, and you have that slash there of 2 you see everywhere means there's 2 signals in the flow. There's a real part and an imaginary part. Does that sound acceptable? I realize if you work in the lab, you don't only think of one signal, right? You just think of a signal. Well, we have 2, mostly in radio, because we're carrying a complex baseband signal, as we call it. So this is what it looks like if I have a signal at FC and I want to bring it down to actually process it through the radio. I just set the frequency to translate it, so I'm going to shift the entire spectrum to the left, because that's what the e to the minus j is going to do. It's going to move it to the left. It's going to negatively shift it. This image right here gets filtered away, and this image moves down and sets right in the passband, and that comes through the radio. So I'm going to try to get this running again. There it is, and the audio did not come through before. Hey, it's working. You can hear it. I didn't want to see that. This is KCME. For whatever reason, FM is not, I'm not getting it in this downstairs room very strongly. And if I was to zoom up there and move to a different frequency, let's just see if I can pick up a different frequency. Okay, this frequency right here, 162.475 megahertz. It's not getting anything right now. This is a weather station that's located over in Manistee Springs. It's a very low power signal, but it's not. I changed it to a narrowband mode on here, narrowband FM, as opposed to wideband. You'll play with these in Lab 6. You can play with these and work with them in Lab 6. And you'll set up the transmitter and a signal generator and receive and then scan each other. Person's on. Do you have any questions on what's happening here? These are fun to play with. I mean, can engineers have hobbies that are related to their discipline? Absolutely. So they're a lot of fun. I first got introduced to them when I had a master's student who worked for MITRE, and he did his master's thesis using an SDR project. And actually you can track, for example, at different frequencies, this goes up to 2 gigahertz, you can track tail numbers on commercial aircraft. And there's actually a community across the country that is picking up tail numbers, and you can go to their website, and if you want to figure out where a plane is, you're expecting a family member or friend to come in on a plane, this network actually tracks and fuses the data and tells you where that particular flight number is based on its tail number, which is being emitted for a part of a safety consideration in commercial aircraft. It's a transponder. So it's based on the tail number, though, of the plane, and then that gets that will get transformed to say Delta Flight something or another it's currently here, and then you can follow it across. It's believable, right? I mean, it's kind of cool. I've done it a few times for family members to see what's going on, where their plane's at. So I have I have that in here. At some point, we'll also look at GNU Radio Companion, which, see if it starts up. This one gives you a complete block diagram. So this one, most of the little tiny blocks in here are shaded out, but I have it set up so I could do RTL SDR right now, and I could receive it and have a spectrum analyzer brought up. Some of the shaded out blocks are for the different radios, like this guy is in here too, and I'll do a demo of this, both transmitting and receiving in a little while. I don't get anything else done if I start playing with all the toys that I have at home, but so I'm not gonna go down this path. But if I set this up on here, I could leave this radio on here, and it would show the spectrum that we were just looking at. Now this happens to be running. So this is just a little advertisement. This is running in Linux. So I'm actually running Ubuntu Linux. And this is the terminal so that I could launch things directly from the terminal if I wanted to. But I installed that on Windows 11. It's very easy to do. And the GNU Radio Companion only works on WSL, is what it's called, on a Windows machine. WSL is Windows Subsystem for Linux, which... Has anybody played with it in here? No? Does anybody use Linux in anything? Okay. Well, I'm going to show you one little thing that if you start playing with Linux, and I have to do a lot of it in my work right now, this little pocket book has all the cheat sheet for all the terminal commands in a Linux environment. To me, it's invaluable because anything you do only occasionally, how does it stick in your brain? It doesn't stick, right? So I refer to this a lot for a lot of the command line stuff. And, you know, I'm making you, for this class, do some command line stuff. So it's pretty much the way things work these days, though. So we'll come back and we'll be in Windows Terminal. In Windows Terminal, the way I have this computer set up, I can bring up a number of different command lines. And this one is Miniconda. So this is how I run my Conda environment. I launch it from the terminal shell. So I launch it from, this one is all set up. And let me just get this. We'll be running Conda in here in a few minutes, or pretty soon here. So this is part of it. This is what Miniconda puts on your system, and then you can bring it up in a PowerShell. Or I'm running Julia over here. I've got a session of that running, and I'm running a session of this other new discovery that I made over the weekend. I learned something new, and then I got sidetracked on playing around with something for Python. It's another type of notebook. It's a newer version of Jupyter is what it really is. But mentioned this briefly at the end of class. I'll just briefly say that wireless communications could be super tiny. It could be implantable, and this is an example of something from at least 5-6 years ago that was a wireless device for interocular eye pressure monitoring. Very low power. It gets charged up by basically light, I believe, is the way this works. Yeah. Energy autonomy, 10 hours of indoor lighting, or 1.5 hours of sunlight. There's other interesting things with electronics, radio, and super low power that's out there that I've talked with companies over the last 10 years that talk about energy harvesting. Is that in part of anybody's senior design project, energy harvesting? You can actually, this is an electromechanical thing, but you can actually have something picking up small wind currents in a room, and you can create very small amounts of power just from that, enough to charge a battery to power a wireless device. I mean, and that's this company that does CO and smoke detectors was interested in energy harvesting for safety purposes. You know, your smoke detector is an annoyance, right? CO detector, the battery runs out, and what does it do? It's beeping at you, and it usually happens when you're trying to sleep and you're scrambling around trying to get a new battery in it or something. So they were wanting to come up with an energy harvesting means for doing that. So that's all I've got on that chapter. We're now going to start our review, and we're going to get into chapter 2 of the notes, and then we can talk about the homework problems, and then I'll be getting into Python here. We're at 9:11. I could take the break early, make this my segue, come back after break. Does this sound reasonable? So I'm going to call it 10 after, and I'm going to say come back at 25 after. I'll give you 15 minutes again. Is that good? Just out of curiosity, where are you going if you want a coffee or drink or snack? Where do you guys go? If you were leaving here, where would you go before you come back?
Mechanical Engineering Center.
Okay. They have.
Right upstairs. Coffee.
Okay. Okay. Go for it. I'm going to see what's going on with my video and just see if it's still going. Okay, so we're going to get started in chapter 2, and chapter 2 is a very long chapter. It's a lot of mostly review material, but it's, like I said, getting into the notation. And I also want to bring up the problems that I'm looking at. So I will put this on the website, but right now I want you to obviously be familiar with all the problems on set number 1. But the 2 problems that I am most interested in seeing you turn in are the ones I want you to turn in. And I'll reiterate this, but I'll put it on the website and it'll be on Slack, because I want you to do the last 2 problems. So it's problem 4, or problem 5, and problem 6 are the 2 that I want you to turn in. Now, like I said, I'll reiterate that. Both of them allow you to use Python for visualization. You can work them. You can always work problems on paper, and that's perfectly fine too. I now have information on some ideas for you to, say, use TYPEST, which is what people did last semester, but whatever techniques you have perfected over your years for turning in things electronically, I want you to just carry on and use that. If you want to explore TYPEST, I put a link to that on the website, and I'll get more into that once we move down into this math modeling stuff and I can jump into Jupyter. So chapter 2 is where we're going to spend some time right now. It's just a collection of all kinds of signals and systems review topics. But then as we get further down in here, and I've got material that's not even in this edition of the book anymore, but it's still around. One of the things we're going to do, though, that is for sure new is this right here. Power spectral density and correlation. That's not something that I know you've studied at all before, knowing what the curriculum is about. So we're going to learn about power spectral density. That's a new topic in this chapter. Like I said, most all of these others are review. Some of these things, like these things at the end, I really don't touch upon until we need them later, although the last one, using the DFT and FFT, is used in some examples that are in the Jupyter Notebook for doing certain types of calculations. And one of the things that is in here, I love digital signal processing, and one of the things that I've been teaching the last 2 falls to come back and help out with is that course. But I look at the study of signals and systems, what we're doing right now. After you finish 3205, you're now entering into the courses that rely upon signals and systems very heavily, especially the math modeling. I look at signals and systems as a 3-legged stool. It's got 3 main disciplines that fall underneath it. Control systems is 1, this class is 2, and digital signal processing is 3. Now, there's a relationship between 2 of them relative to the third. Controls and comms are kind of side by side, different aspects of using signals and systems to create solutions for helping our society out. I mean, remember I said that's what engineering really is. We're creating things to help our society out. So controls and communication systems are big players in that. Digital signal processing is big unto itself in certain aspects that maybe don't fit into those other 2, but really digital signal processing to me is the glue, or the ability to create these new things where everything is algorithms and discrete time processing as opposed to analog circuit design. So DSP factors in, and DSP factors in hugely in this class too. And I'm not teaching you DSP, but we are going to be using it because you've all had a background in it already. How do we model things on the computer? We have to discretize things, so they will become discrete time signals. I won't be emphasizing the things that would get emphasized in the modern DSP class, but still, they are factors. Just reminded myself that I wanted to show you a project that kind of highlight something that I did last semester. I'm flipping over to the Modern DSP website, and I'm looking at Python projects, and project number 2 was a channelizer for AM radio, which we were talking about just a little while ago. So for this particular project, I developed in Python this numerical model that implements this channelizer. So this channelizer could be thought of as part of the front end in a software-defined radio. And what this channelizer allows you to do, and where I'm working at ARCA, a former student of mine has a channelizer that's being used in projects. Channelizers have applications mostly in government and military applications, but I thought about creating a component in software for channelizing. So I bring in a signal over here. It's a discrete time signal, but we could think of it as starting out as an analog RF signal. We then process it into subbands, and those red subbands there are just the ability to center possible signals that might be arriving in different subbands. So we're going to do digital filtering and parallel processing, and this component has got the capability of having an even number of bands, odd number of bands, and the fact that I don't have a uniform spacing shown over there is just showing the possibility that active signals might exist in those bands. But at the output, we get a stream of channels coming out corresponding to each of the subbands that we've broken the signal down into. So we're going to process a narrow band and then another narrow band. We're going to process these all in parallel. So I'll put that into the application, and it uses fast Fourier transform filtering ideas that are more of a topic from the other class. But this is what the system looks like in the end. And I could have you I could reconfigure this project from last semester into a project that you guys could work on in a different way using the same components. And I would just tell you how to drive the components. So here I assumed I had an RTL SDR, and I actually built this up using GNU Radio. So I built all the hardware part of it up and the software for the SDR, and then I captured a very large file. It was like 500 megs of capture that I distributed on Slack, and I know that works. I could give you a large capture. Does that sound like you're doing a covert operation working with a capture? I mean, you could think of it that way, but you're going to get a capture and extract intelligence about it. But in general, it'd be running in real time. But for the purposes of this class, a lot of things we'll do for simulation and modeling, we'll be working with, could be generating test vectors in Python or having them pre-generated. In this case, the capture was obtained by me, and I give it to you. It could happen in industry. It happens all the time, actually. Give me a test vector. I want to test out some ideas. I want to develop some new algorithms, some new way of processing signals. So here, I did a capture. It covered the AM broadcast band from 470 to 1670. I broke it up, the channelizing up into first 5 bands at a sampling rate of 1200 kilohertz, 1.2 megahertz per second. And I would downsample and have 5 bands that captured subbands, 5 subbands of the AM broadcast band, and then channelize a second time. And now the second channelizing bank, each one of the bands there is 1 AM radio station. So at the end, I've got 120 AM radio stations all coming out simultaneously. Now, in an AM radio application, listening to sports or talk radio, there's not really a lot of exciting things on AM radio. You would only listen to one channel at a time, but from an intelligence or whatever reason, you might want to be monitoring everything at the same time. Does that make sense to everybody? Monitoring, eavesdropping, whatever you want to call it. We do things like that. Or maybe we don't. What do you think? We do things like this. We have cameras everywhere now too, right? So we're just so wired up. reminds me walking past a neighbor's house with my dog, they have to have their speaker on their camera now to say, "You are being watched." And I'm like, just shut up, you know. I know you're watching me. They don't have to announce it or anything like that. To me, it's irritating now that they have audio on their cameras. Maybe some of you have one, so maybe I don't want to offend you, but I just assume it's happening, right? I was in an accident over in my neighborhood, and the capture allowed me to turn it to the police and the insurance companies, and I won my case against the, you know, the arbitration board had to review. I was not at fault, but the camera helped prove to the insurance companies that somebody ran a stop sign. They were probably on their cell phone, not paying attention to driving. I didn't have the need to know that, though. At any rate, this is kind of a cool thing to be able to do that. So just giving you an idea of where there's a lot of DSP involved. And then at the very tail end of this is a very simple demodulator of the AM radio signal using the absolute value of a complex quantity and then a DC block. And we'll understand a little bit about how that actually recovered the AM radio station signal back to a playable speech signal. The first level of processing, though, in this case, looked like this. These were the 5 subbands. So the taller signals there are the ones that were the local AM stations here to Colorado Springs. And then when we process down further into one of the subbands, like this is one of the subbands of 24 channels, there's noise coming in from the receiver, just like we heard noise, right, when I was playing the radio. Be convinced, maybe by that end, there's both that noise is always there. We don't have a signal that's free of noise. Maybe it's low that doesn't bother us, but it's still to be contended with. But here, there were 2 strong signals. The others were spurious, or this was recorded at night, so they were skip signals that were coming across the country, just barely intelligible. But you can see that there's 2 strong signals, and then pick up those subbands out of the 24 and then demodulate to get the signal back. Now, since I'm on here, I can't resist, you see some leakage in here. This is from another subband. It has to do with the integrity of the multi-rate signal processing. And those are things that are happening in the discrete time implementation, but they would still happen in analog, pure analog implementations. We like them, in general, we like them better in DSP than we do in analog. Why do you think that would be so? I'm just curious if you're thinking, what makes digital signal processing better than analog if we can do it in DSP? We can program it, and it's based on finite precision arithmetic, and we can understand the limitations of our filters and our algorithms, and we just have it more contained, whereas analog, and some of you are probably interested in analog too, and I'm interested in analog, and I did analog a lot. There's just more variabilities in analog design, and you'll see when you measure the filters in the lab that they're just not that perfect. They're not working that well with the off-the-shelf components. They work, but they don't work to the same degree that DSP can do things. So you might say I was converted to DSP a long time ago in terms of thinking I'd rather do things in algorithms, and it's a fun occupation too. So at any rate, I thought I'd mention that or bring that up. So we have 2 different types of signals that we classify into. There's different classifications, but this classification draws the line between deterministic and random. So deterministic is the main focus of this class, but it provides a lot of opportunity. This particular, this is really a very generic signal, and you've been studying sinusoids all along, but now we're going to put the amplitude in front is a function of time. That'll be amplitude modulation for us. Then the other type of modulation that we'll bring onto the scene, we'll making the frequency F naught here a function of time, and or the phase a function of time. And that brings in phase modulation, phase and frequency modulation together. So that's really things that we're going to do. These can be in pure analog form as they started off historically, or we can send things digitally. In other words, have an encoding scheme where we take and represent things, finite number of frequencies, phase states, and amplitude states. So it's not that we like one over the other. We've just morphed mostly from digital analog to digital types of modulation. But this is what is sort of at the core of everything in this class. Does it seem too easy? It seems easy on the surface, but putting up a signal that's very complex in terms of how do we demodulate it is part of the challenge. We create signals, and then we have to extract the information from that signal, because the RF carrier is exactly that word. Carrier means it's carrying the information from point A to point B. Another thing that we do in SATCOM a lot is we have maybe a telemetry waveform that lies co-channel with a ranging waveform, because satellite communications always needs to know range between the ground and the device up in space. So one of the things I'm working on right now is exactly that. It's a combined telemetry and ranging, and they put them on the same frequencies. And you're saying, wait a minute, they're going to interfere with each other. Yes, they interfere with each other, but it makes for efficiency in spectrum allocation. And then you can do fancy things at the end of recovering one first and then getting an estimate of that one to go ahead and go through another set of algorithms to subtract out the interference from the other component that's maybe weaker. And it's like shooting yourself in the foot, but you say we're going to do things because we want to make things efficient. So if I was you, I'd say, that sounds really great, because now I have more work to do. You know, we're going to make it more complicated. We're going to utilize the spectrum efficiently, and we make things more of a challenge for us. Okay, the other types of signal that we have is random signals. So random signals take on random values with probability characteristics. A random signal really is the next step beyond the thinking that you go through in 3610, and that would be first probability, the axioms of probability, sample spaces, rolling dice, drawing cards, all the other things that if you had probability theory already, you know what I'm talking about. And then we assign, then we create a random variable after that, which might be able to take and convert, say, the face on the dice into numbers, and then those numbers are encoded into a waveform, let's say, like for digital communications. But then the next level above that is to create a waveform itself, which is steeped in probability theory. So it has the sample space for the probability, it has the sample space associated with the random variable, and then it makes the random variable a function of time. So this gets added in along with the randomness of the bit pattern or whatever it happens to be. And then the other thing that mostly shows up in communications theory for the random is the signal itself that we desire, but we also have the undesired, like the noise that we were listening to before. And that's just due to the analog circuitry having random electron motion due to not being at absolute zero. That would be nice to be cool everything so there's no random electron motion, but is it practical to do that even? So we deal with it, and that's the history of communications, is dealing with the noise that happens to be around. So specifically, I'm not supposed to be teaching random processes in this class, but we will have randomness thrown in our modeling and other things, because otherwise, you just don't have quite as much fun, I don't think, if you leave it out. Question.
What are some of the examples of wave signals that are random?
Say that again.
Wave signals that are random. Are there some wave signals that are random?
I didn't quite. Weird?
I'm saying, are there some wave signals?
Oh, waves.
Yeah, that are random.
If it's propagating a signal through space, it's got a random behavior to it all the time. I mean, what I didn't say, I think what you're getting at, this thing I circled in red, that would be a deterministic waveform, thinking of it being as a generated by a function generator in the lab. I can turn on a piece of test equipment, I can generate that signal very precisely. We have those in the lab right now. But when this signal travels through space, and we're looking at the phenomena of the channel itself, we're going to get not only additive noise onto this signal, but just that signal itself. There'll be fluctuations in the oscillator frequency. It will not be stable, so we'll add phase noise and long-term drifting of the frequencies. The propagation medium, if we're moving and driving in a satellite situation or driving your car down the highway, there's Doppler. And then there's multipath. There's more than one signal that arrives. So is that kind of what you're getting at? We have multiple signals because we just have multipath. We're living in an environment here on the Earth, and when we transmit, we're going through different things around us that create reflections and refractions and so on. It's pretty exciting. I mean, you're saying, this is so hard because it's got so many factors. You're right, it is. But we can start easy, and then we see, what are the practical limitations. We come up with a scheme, and then we say it's not going to work well when we have real factors included. So that's the thing about modeling those. We're always building a simple model, and you do this in everything you do in electronics. You try something simple, and does it work? And then you have a proof of concept, right? And then you take it into a more realistic setting, and then you see, can I still make this work and still get value out of it? It might actually fail, like pulse oximetry. I'll just use that as an example, because I had a design team that was working for a doctor on a specific type of pulse oximetry device that he was desirous of, and how do you attach it to the finger, and some of the other factors. I'm trying to remember what went on in that project, but it was an interesting project because the doctor was the sponsor, and he played with microcontrollers and did a lot of electronics on his own, and he was trying to tell the team, I want you to use this specific, this, and this in terms of your parts. He was very exceptional, a medical doctor that was very involved with electronics and was trying to tell the team exactly use these parts and make it work. And in some senses, that thwarted the team because they were like, can we just pick something? Or I had Colorado Springs Utilities sponsored some things too, where they wanted certain devices to be used. And that's the very nature of capstone design, though, I guess, is you have to work with customers and you have to design and build to suit their constraints and system, right? You can't just say, I want to do it this way. You got to live with what the customer tells you they want and how they want you to do it. It is a reality, and most everything that you will work on will be something legacy. You're not going to be out there creating your own idea. You're going to have to live within some framework. So quickly getting started, just remembering what is a periodic signal. In the continuous time domain, it's periodic if you can take the signal, pick it up, slide it over by so many seconds. It's a little bit more involved in the discrete time domain because you pick it up by an integer number of samples and move it over, but we're not going to drive so heavily on that. And then on the computer, we can always make a sequence be periodic, but we do definitely have asynchronous behaviors that can happen, and a periodic signal doesn't really allow for that. Periodic signal says it's just going to keep repeating itself. It doesn't have some asynchronous aspect to it where it slides along because of a clock oscillator slightly changing over time. But that, of course, shows up in the real system. We also have aperiodic signals, and this is an example of an aperiodic waveform that the book likes to use. It's called the pi function, or capital Pi, and it's defined as a waveform that's a pulse of amplitude 1, and it runs from -1/2 to +1/2. So I'm going to see if I can make, that's not going to work. I used to have my old tablet, and this doesn't want to work. My old tablet used to have a digitizer on the screen, and I just have this pencil now, which is just the rubber tip capacitor. I can put my finger on the screen, but I can't draw on it without it having issues. So I can't draw very well here. So the way we end up using this is it's capital Pi t over tau. So we put a scaling factor in there to make the pulse width have a full base width of tau. So it would go from -τ/2 to +τ/2. Periodic sinusoid is shown in here, and then a random signal is shown in here. These are just pictures. We're going to unfold more special types of test signals here. We have two in the very beginning, though. We have the rectangular pulse function and the triangle pulse shape, both of which show up in homework problems 5 and 6. And if you were walking in late, those are the two I want to be turned in, 5 and 6. I will put all that on the web. It will go on Slack, and I'm going to draw the line of saying if it's either Friday or Tuesday when we get to the end of class, okay? Because I don't know how I feel and how you feel. I have to get Python up and running here yet too, to get you going on that. We will, of course, think about phasor signals. Complex sinusoids in particular are very big in this class. So in the review here, the book has, here's our complex sinusoid. It's got an amplitude A, radiant frequency omega naught radians per second, independent variable t, and then it's got a phase shift of fixed value theta thrown on there. We don't really think about it rotating like in the sense that you did when you first saw this in circuit theory, but it is a sense of the reality here. We have the real part of a complex sinusoid is the cosine, and this is representative of what goes on when you transmit a signal and receive a signal that's been sent, propagated as a wave over space. So we have the in-phase and quadrature part, and that's where the complex sinusoid is very helpful, and that's what you saw in the radio example I was looking at earlier. But we're perfectly okay in the lab with just saying we want to have a real sinusoid and we want to just generate it like this. The need to actually think of it as being a complex sinusoid will come as we model things in real systems that happen in software-defined radio primarily. Euler's identity shows up frequently, just the same. And then the other thing that shows up in the very beginning, and this is the first homework problem, is just line spectra. When we have a single sinusoid, we can have either the one-sided or the two-sided. So this is the line here just saying we have the single-sided spectra, which is what you experience in the lab with the Field-Fox spectrum analyzer. And on paper with the math, we tend to like having the two-sided spectra more often, and they're related to one another. If it's a real signal, it's got this nice symmetry property. We can take, for the single sinusoid that was shown up above, you can have a spectral line at minus and plus f naught, and you have half the amplitude, whereas if it's a single-sided, it's just displaying the whole amplitude at f naught, and the phase is split asymmetrically between the positive and negative. And this comes about because of the way Euler's identity expands, that we saw up here. This A cosine expands into those two components. So I assume this is like, okay, I've done this before. I can draw a picture like that. I can sketch a picture. The first homework problem is just basically this. It's very much this first example right here. A couple sinusoids expanded into Euler's identity so you can find the two-sided spectra, and you just expand it in Euler's identity, and so now you can see what the amplitudes have to be on the positive and negative frequencies, which is what the complex sinusoids give you. The e to the plus j is on the plus side, and the e to the minus j is on the minus side, frequency-wise, and convert it to a line spectra picture. I think one of the things I always think about, and since I haven't taught this for 5 years, I'm not really, or 6 years, I'm not really tuned into the misunderstanding or understanding that you already have from the previous class. But a really good thing to mention is when you sit in your car and tune your radio, you tune your radio to a positive frequency. You don't tune on to a negative frequency. So why do we have to have the negative frequencies showing up when we talk about line spectra and spectrum in general? It's just the nature of the mathematics. Can't escape it. And it turns out to be more blatantly clear when we work with software-defined radio. So actually the fact that we now do SDR on a regular basis, the fact that we have positive and negative frequencies present in the spectra is omnipresent, and it serves a purpose. I think when you first learn about spectra, you say, why would we only want to care about the single-sided spectra versus the two-sided? And it's just simplicity. And a measuring instrument like a spectrum analyzer in the lab, it is just the positive frequencies, but behind the scenes in the math, there are the negative frequencies. And in lab number 2, you work with modulated signals, and you work with pulse trains and things, and you definitely can see how the analyzer is maybe only saying the positive frequencies in here, there's a negative frequency here, and when you bring something too close to 0, something will cross over from the negative side into the positive side on the spectrum analyzer itself, and you will say, oh, that really is there, and I can't escape that fact. In other words, you can't just chop it off and throw it away and say it doesn't exist. It'll be something that'll be a curiosity, and I make sure, those of you in the lab at least, that you will be exposed to that. You will see this strange thing happening. You only see the positive frequencies, but you'll see that the influence of the negative side is actually going to show up when certain types of modulation are present. We do have to work with singularity functions like delta, and they are abstract in the continuous time domain. It's nebulous because it has this fundamental property that when you integrate a delta function, you get a functional value if the delta is on the interval, say here between t1 and t2, and you have this property that it's 0 except at that point, and you're tempted to say that it must go up to some value at that point, t naught. Is that value infinity, or does it have width? So does anybody want to give a testimony on how they feel about delta functions in the continuous time domain? Do they make you feel, uncomfortable or nervous, or you just say, hey, I can go with it because math is our friend, it's not our enemy? Anybody want to say anything? Are you good with them now? Just think they're your friend, and they're operationally, we have what I like to think of as operational math. Mathematicians take them very seriously and have probably maybe more trouble with them than we do, because we can take a more laid back operational view of it and just say, I can cope with this. I can use this sifting property idea to get a functional value out, and if I go down here, I can make a test function for a delta function, something that has finite width and finite height, but the area is 1, and then I can do some experimenting with the math and take a limit, let's say, and see what's really happening if I have to. But operationally, these are, this is kind of one of the main things that you get to do with the delta function is you get to do a sifting property, and you can use it in the time domain in this fashion. We do use delta functions in the frequency domain, and there again an idealization. There's theoretically a delta function at a particular frequency f naught, like the line spectra, but really it's a delta function that's, it's not an idealized delta. Ideally it's a delta function, but in reality it's not, because the signal is not 0 hertz wide, and it's not standing perfectly still. It's got some bandwidth associated with it, just due to the imperfections. I do have properties, because the book goes through them. Most of these properties are not that important for our needs. This scaling property was built into one of the homework problems. It's just an exercise just to know that you can do this. Likewise, the derivative property is built into a homework problem. It's not something we're doing really in this class at all with derivatives of delta functions. It's a somewhat bizarre thing to actually get involved with derivatives of delta functions. You have something called a doublet when you do that, because you have a spike up, so when you differentiate, you're going to get a spike when it rises up and a spike that goes down. And the only way to really see that is to create a rectangle pulse and then differentiate it in a approximate way where it will get the doublet, and then it comes together. I'm not going to really go through that, but have you ever talked about things like that in 3205, a doublet, where you have a spike up and a spike down? It has its applications in other linear systems domains. Other test functions can be a sinc function. The magnitude of a sine x over x function can be useful too. The next level of singularity up from the delta is the integral of the delta, and that gives us the step function. So we have these two things go back and forth, where you differentiate a step function and you get a delta, and you integrate the delta and you get a step. How can you actually differentiate something that's not continuous at t is equal to 0? Well, we have to do it operationally. Again, we have to say, we'll just say that if we had a test function in there, which was a rectangle of some width and height, we could, in an operational sense, take the derivative of a function jumping up and just take whatever that jump is and let that be the derivative. And then when it jumps down, we take the derivative, we get a negative value. So we can form an approximation for this idea of the ideal step function. And an ideal step function and an ideal delta function are just abstractions that are useful for modeling. We don't want to nail them down. We just want to use their operational properties. And I guess I want you to be able to just roll along with it, because that's what we have to do. We use it to help us make life easier, not make it so crazily detailed that we can't just back off and say, we'll just use these operational properties and we'll be able to do modeling with them. I mean, the step function onto itself is nice for modeling, but can I generate that in the lab and be an ideal step? No, it's going to have a finite rise time. It's not going to instantaneously rise up, but approximately so. If we back away from a finite rise time step, if this is what our step actually does, and we stand back from that a really, really long ways, it'll look like it just goes bang, bangs up, comes back down again. So it's good for modeling purposes. And this was the example of the doublet idea, or the differentiating. I did put that in the homework, but I'm not planning on doing anything more with it other than just saying it's just something for review and discussion. Okay, the next topic is signal classifications. And you're saying, wait a minute, we just classified signals as random or deterministic. Well, that's one way of classifying them. The next way of classifying them is either as a power signal or an energy signal. So we can have power signals that are random and energy signals that are random and deterministic, of course, too. So we have to break things down into power, classification, and energy. Most everything that we do in radio communications involves power. It's some continuous waveform that keeps sending something, whereas energy might be just one burst of something. Like when I was talking about how you might be monitoring a nuclear underground test somewhere on the other side of the world with seismic sensors. That would be more of an energy type application. Or in digital communications, we might send a string of bits with pulses representing each of the bits in the transmission, and the average power of a bit stream would be some value of watts, whereas an individual bit might be represented with so many joules of energy. So we have the needs to be able to think about things in terms of an average, power, and then an energy of a single bit or something like that. So power is voltage times current, and then we have R thrown in there if we want to do it with I squared R or V squared over R. And most of the time we're going to do things with a per ohm basis. So in the book it's always going to be 1 ohm unless stated otherwise. In the lab you already learned last week that it's 50 ohms because we're working in a 50 ohm measuring environment. So the R is really not talked about too much except when you're working in the lab, when you're working with a 50 ohm system. The way all of the modeling in the book works is assuming a 1 ohm system, and it's just for the convenience of the math. When we want to put it into an instrumentation or a real system, we'll just bring in whatever that impedance level is, and we'll go from there. So fundamental equations that you've seen before would be energy is this upper equation, and power is the lower equation. So we're averaging by dividing by the time. So we get the average power, we get the energy of the waveform. And this is what classifies things. It's an energy signal if and only if the energy is between 0 and infinity, and of necessity that means the power is 0, and it's a power signal if the power is between 0 and infinity, which necessarily implies that the energy must go to infinity. So we have those two different divergences, and those are in, which problem has that in it? I think it's maybe, I've got my tablet that's got the solutions in it here. I think it's the third problem. Yeah, or no, problem 4 says classify following signals as energy or power, and what you do when you work that problem is you're just seeing whether or not these two properties hold. And you've done that elsewhere in like 3205, right? Does it have finite energy? Does it have finite power? I think there's another problem that involves sinusoids, multiple sinusoids, seeing if it's periodic. So you have to find least common multiple so that you can form, you know, if it's like a 5 hertz signal and it's a 25 hertz signal, what is the period of that signal? It would be 1 over the fundamental frequency, so it would be 1 over 5 hertz, because 5 times 5 hertz is 25 hertz, things of that sort. There's a problem on that too, but it's kind of obvious. You can play around a lot with the real exponential a e to the minus alpha t, and you can discover that it can be an energy signal, it can be a power signal, and it can be a neither signal, because it can be a signal that has infinite power and infinite energy, and that's not a signal that we would generate. Can you generate a signal that has infinite energy and infinite power? No, I don't think we can do that. That would be marvelous for energy conversion, right? We could get something that could be infinite. But that's sort of, I'm rambling on this stuff because it's like the math can do lots and lots of things, but can the math do everything? Figure out what's sensible and what's not sensible? It can't. So you have to be able to use your brain. And what was I listening to? I listen to Sirius XM a lot in my car and at home. I stream it. I'm trying to think. Somebody was making a joke about AI, and I can't remember what it was, so I'm not going to say it right now because I'm going to mess it up. It had to do with artificial intelligence versus my intelligence. So,
Natural stupidity.
yeah. It was very cute though. It was a play on words, but it had to do with artificial, whereas let's go with my intelligence, my real intelligence versus artificial. But I don't remember what it was now. At any rate, we have to think realistically on things. So this is just a neat little mathematical example about how if you let alpha equal 0, then you get a signal that starts at 0 and goes off to infinity. So what is the average power in that signal? It's a squared over 2. And if you didn't have the unit step function on there, what would it be? It would be a squared, which would be the DC power, just a constant voltage for all time. But if you let the voltage be a for just half the timeline, it would be a squared over 2. But that's assuming you're expanding from minus to plus infinity. I mean, so you have to, again, think in a common sense about that. But that is our definition. If we go back up here, energy is all time, power is all time. So energy in a cosine wave is infinite if we assume that it's running over all time. And then if we go ahead and normalize by time, we get a squared over 2. So this you learned a long time ago. Don't forget it. It's very fundamental and it's very valuable. It's a squared over 2 is the power in a sinusoid, where a is the peak amplitude. And we're assuming a 1 ohm system. Okay, the next little thing that I'm not really going to go through is generalized Fourier series, how we can get a handle on a spectral representation is through a Fourier series, but we're going to see that the Fourier transform actually can handle both periodic and aperiodic signals. So we're going to, I'm more of a person that would like to have everything in the Fourier domain, not really have Fourier series, but it's a stepping stone to see about periodic signals. And this topic used to be in the book, the generalized Fourier series. It just says, let's think in terms of a vector space and that we would like to represent something in terms of basis functions. And I think everyone here takes linear algebra, right, from math. So you've seen the idea of basis functions and vector spaces. So generalized Fourier series is exactly that. It spins off of the idea of vector spaces and orthonormal basis functions. So I'm just going to kind of get to the punchline here with a picture. It says we have this sinusoid right here, and we would like to represent it in terms of 3 basis functions. The basis functions would be a pulse like this, a pulse like that, and a pulse like this. This is not the normal Fourier series that you're thinking of, but it's a valid type of expansion. We would represent using orthonormal basis functions, and that's what we've got right here. So we have functions that are orthogonal to each other on the time axes. They don't, in this case, they don't overlap each other, so they're orthogonal to each other, and then they can be normalized to be of unit area. So we could think about how these three basis functions could approximate that sinusoid. And without going through the detailed math, I'm just showing you the picture, we could get Fourier coefficients then in terms of those basis functions. And the three basis functions would form this red waveform. It's not something that you have to do in this class, but I'm just letting you know what generalized Fourier series are. So the Fourier series we care about, though, these are the basis functions. They're the complex sinusoids. So in the case of the sinusoid we were just looking at, it takes two basis functions, one at a positive frequency, one at a negative frequency, and we can calculate those coefficients from this formula. So we have, fundamentally, this is our Fourier series idea that we have. Any function can be written as an expansion of coefficients multiplying times e to the j and omega naught t, and the coefficients are calculated through this integral over one period for periodic signals. And I know you've seen this in 3205. You probably don't care for it a whole lot, but it is sort of it's the basis for any periodic signal we have. We can think of it as having a Fourier expansion. And it comes up in radio because we think about harmonics being generated from carrier oscillators and things. So we want to think about how, if we don't have a pure sinusoid, we are going to have other harmonics present in a waveform. Like, suppose we have cosine squared, we multiply that out, and we can see by inspection pretty much this is its Fourier series expansion. Because we can see that when we multiply it out with the trig identity and then expand the cosine with Euler's identity, we can see we have three coefficients in the Fourier series. We have a half at DC, that's x0. We have a 1/4 at x sub 2. And then we have a 1/4 at x sub minus 2 for the Fourier coefficient in terms of the basis functions. So that's really what I want you to be thinking about. You don't have to drive in and do these expansions where you have to find coefficients. I don't know if that brings back bad memories to you or not, but it does to me, because I had to do this in school. And then, not in this class do you have to do that. As a matter of fact, it's on your crib sheet, I think, and the crib sheet that I have. And you need to have knowledge of these things in the lab. This is a new concept, though, right here, the time average operator. So we end up using this a lot throughout the entire semester. And this is just an example for a signal v of t. The time average operator says what's on the right-hand side is this limit of an integral of 1 over 2t times minus t to plus t. But what we're going to see later on is that v of t can be replaced by anything we want. It can be a waveform, it can be a waveform squared. This is just the time average of whatever is put in those angle brackets. And that's what the time average operator is. So Fourier coefficients, for example, can be viewed as a time average operator, where this would be your Fourier coefficient, where you're plugging in x of t times e to the minus j n omega naught t. So it fits for that. And Dr. Ziemer is famous in the book for just using that. I mean, it's a shorthand notation. Now that you've seen the time average operator, it'll pop up. It'll pop up in various places. You just have to keep that in your head. But if we're creating a model in Python, we can operate on a vector in there or an array in there with mean. We can do the mean. And if we want to do the square, we can do the squared mean. If we want to do the squared mean minus the squared value minus the mean squared, we can get the variance using the VAR operator. So we have really quick access to this in a generation means on the computer too. So I want to get down to something that I can do. We have the pulse train, line spectra. This is not showing up in the homework. We have I'm going to skip ahead just to put something down here from the Fourier transform, and then I'm going to jump over to Python. So we've already seen this guy here, this rectangular pulse, and this is the Fourier transform of that, but I'm just looking at the pulse. And then we also have, for whatever reason, when I wrote out my notes, I didn't put this all in the same spot. I just want the triangle pulse. So those are two things that show up in the homework, problems 5 and 6. So the triangle pulse is like this, as opposed to the rectangle pulse, which is just a constant amplitude. So the things to know about these two pulses, the way they're defined in the book, are the denominator there, tau, is twice the base width of the triangle pulse, whereas in the rectangle pulse, which I was looking at a second ago, it's the full base width is tau. So one is like width 1, the other is a width 2. And why do you think they're defined that way? Think back to something from signals and systems in particular, or convolution. What happens when you convolve a rectangle with a rectangle? Your brain should be smart on this. It's going to get smart again. You convolve a rectangle with itself and you get a triangle, right? And what is the width of the triangle base? It's twice the width of the rectangle. So these definitions come from that, from the idea that triangles and rectangles kind of go together with convolution, and the twice the width is not to drive you crazy, it's to relate to the idea of how it comes about when you have a convolution. So not a lot of time left, so I'm going to jump over to Python. I asked you to get Miniconda installed, and as I was pointing out here earlier, I do have it on a flash drive that I downloaded because I put it on this computer about 2 weeks ago. So I do have a Windows version of it. The Mac version is going to be different, of course. But you can get that from the link that I have in the syllabus. So you need to get that installed, and then you need to follow the instructions that I have on the website, which are right in here. You're going to create a virtual environment. And so once Miniconda is installed, you want to go and you're going to see base listed over in here. And that means you're in the base environment of the Miniconda that you put on. You do not want to install anything into the base because you want to keep it just clean with whatever it got installed in there when you installed Miniconda. So what you want to do, though, is make a virtual environment. So you're going to, from your prompt in your terminal, you're going to say conda create, and you're going to follow with this command line, and then you're going to switch from the base to this virtual environment, and then you're going to do a bunch of installations of packages in Python. And so I'm running in my terminal, but after my Miniconda was installed, it put this amongst some other prompts on my system for Miniconda. It put one to bring up the command line, the other one to bring up the PowerShell, and I happen to like the PowerShell prompt much better, so I have the PowerShell prompt right here. And if I know this from those instructions we were just looking at, environment list, I can just list my environments that I have running right now out of my Miniconda. Base is what it put on when I installed Miniconda. I gave you instructions on how to create DSP-COM313. That's my primary environment for running Jupyter notebooks. I was experimenting with Marimo Python notebooks since Saturday. And why did I discover Marimo? It popped up in one of my blogs that I read, and it said, this is the notebook. Well, I gave you a link to it here too. I gave a link link to I don't want you to get sucked into everything that comes along, but I tend to get sucked into new things and I want to investigate them. So I said, what is this all about? It's pretty cool. It's actually very cool, but I think Jupyter is a better way to start if you've not done anything with Python and computation notebooks. I think you can really only appreciate something like this Marimo because Jupyter's been around for over 10 years now. And what happens when anything gets invented or gets created, people start finding things they don't like about it, and then pretty soon people start saying, I'm going to make something better. And then they release something. So do you believe you would do that? I believe every one of you would do that because that's just the nature of an engineer. I can make something better. True? I mean, you just feel that way. That's what you're empowered with that, I think, being a student and being creative. So at any rate, I'm in the DSP-COM environment, and I got in there. If I just wheel back, I will see that at one point I typed conda activate, so I activated this environment. And you can see when you do this list that I did, there's a star, and that's telling me that's the environment that I've got activated right now. So from here, I would just type Jupyter Lab and at the terminal, and it's eventually going to launch it. So it's launching it, and it's now brought it up in my browser, and make sure I have the right one in here because I've created a few of these. Yeah, this one will work. So the notebook comes up, and the first thing I do in this cell is I'm creating, is this big enough or should I make it bigger? Be honest. I'll make it bigger if you want me to blow it up some. First thing you have to do in a Jupyter notebook is you have to get some packages from Python installed. This is reminisce of C programming, and you've all done C programming where you have to do an include of some sort in C. Python, you have to do an equivalent of an include. Yes, MATLAB had all that stuff packed in when you installed it because it's commercial, pay-for software. So Python, you have to do your includes, or they're called imports, or a from import. So to make life really easy, I'm importing all of the NumPy functions into our workspace. So this is actually a bad practice, but I'm doing it to make it easy.
What is the path to the notebook? Because whenever I open Jupyter, it just goes into like a generic launcher.
Yeah, so you have to move it somewhere. Usually what happens when you create a new notebook, you get an opportunity to save it. So here, I know you can't read it exactly, but you can see it says Documents, Courses, ECE 5625 Notebooks. If you were to do a new launcher, right now it's going to launch and create things into this folder I already created called Notebooks. If I do this, I will create a new notebook from scratch, and what's going to happen, in my case, it's already got the right address in it, but what you can do is you can go down here, you can rename your notebook, and you can actually, ahead of the name of the notebook, you can put a path in there.
Gotcha.
Does that make sense? And of course, you can open here, and you can see, you can navigate around from here. Right now, I'm down into this folder called Notebooks, but I could go up higher. I could go up, in my directory tree. You want to start it at the highest level possible so that way you can move around and point in to store something. And I probably told you to do that, and now you're sitting way up high and you want to push it down somewhere. It'll create, this is what it will do. This is what it did for me probably 2 weeks ago. It created an untitled notebook right in there. And I should have moved that one if I'd wanted to. This one is not what I just created, but this got created by me by accident probably. And you might have done that too. Any of you might do that. So you just have to kind of get this moved into an area where you can find it again. Definitely find it again. So, okay, so this is Python, and it's JupyterLab in particular is what it's called. And we have to import packages, and then we run Python code in what are called code cells, and we write documentation in Markdown cells. And remember, I told you Markdown is simplified HTML. You can just type that in Google, and you can find, you know, instructions on how you can type a Markdown cell. But I can double-click on this, and you can see exactly how I type Markdown. You can see I'm in a Markdown cell. This is just how you can format things in a Markdown cell, and I hit Shift-Enter, and I'll close that cell up again. This cell here is a code cell, as you can see, and I can run it by hitting the arrow. I hit Shift-Enter. I'm a person who would rather just use the keyboard if I can at all possibly do that and minimize the use of the mouse. So I'll hit Shift-Enter, and see this dot is filled in. It's busy. It's trying to follow all these commands in Python right now, and it's done. It got clear, and a 1 showed up over here. And if you're wondering what this hover mark is, or a hover mark up here is, you can reorder things if you want to. That's just kind of the way the notebook works. You can reorder stuff. You can put cells up above, cells down below. These two things allow you to move cell up and down by 1. You can create a new one above and below, or you can throw it away. I use keyboard shortcuts. If I want to create a new cell, I go Control M, B. Oops, I did the wrong command. I didn't want to do that. And I'm going to forget about what I just did. I have to sit at the keyboard and my fingers just do it, but because I'm thinking about it too hard, I actually typed the wrong commands. But you can type commands right at the keyboard to create a cell above or below, and then you can do another keyboard command to make it a Markdown cell if it's not a code cell already. So here, I just said a²/2 is a ½ watt. I just did a calculation in Python, and I just said, okay, I'm going to take 10 times log base 10 of a quarter, and I'm going to calculate that as a value, but I'm going to print it in what's called an F string. It's something relatively new in Python. There's different types of strings that you can print with. And you did see last week I pointed you to the Python basics, which is on, if you're new to this programming language, just open up this, and this has got the really basic stuff in it about the language and how it works. So it has a lot of really basic stuff. I haven't updated it for a few years. There's lots of tutorials on Python floating around out there, but we're down here. So the F string, and it's called F for format. You might get mad at it and decide you don't like that as the name for the F in there, but I thought about that. Some people probably don't like F. At any rate, format string. So what I can do is I can format a text string with variables. So I'm just giving you an example. I enclose a variable piece of XDB, and then I put a colon behind it, and I say, just like in C, if I was formatting a string using sprintf or something like that in C, I can put in what the width is. I have 1.2 and F for float. It'll automatically format it, but I forced it to do that. I run that cell, of course, and it gives me that. Down here, I just say, let's create a sinusoid. So I'm just going to create a sinusoid. I'm going to give it a frequency of 2 hertz, amplitude of 1, and I'm just going to create a vector. And if I hit Shift-Tab when I'm over a function, and this is a NumPy function, it would normally be preceded by NP if I would have imported it as NP, but I imported everything, so it's just in my workspace. So a Shift-Tab in the notebook will just open up the help. So you can see what A-range is all about. It'll generally give some examples down below. It creates an array of floats in this case. So I create that. This is a working vector then. And if I was to put a cell above that, and I wanted to see what is in here, I can just type T, run it, and I didn't run this cell yet, so I didn't generate it yet. I'll run that, but now type T, and it's a very long array. It's got 8,000 elements in it, so it doesn't try to print the whole thing, but Python is like C, it uses square brackets, and you can use a colon operator. So if I just typed colon, it would start automatically at 0, and I can print like 10 elements of it, for example, using the colon operator, which is very much like MATLAB. It's different from MATLAB, but it's also the same. And if you're not much of a Python user at all, you can get some of these conversions. I guess I did not put that in here yet. I'm going to jump over here. If you're ever looking for something, I haven't moved everything over. I guess I don't have it in here either. I have it somewhere on here. Right now I can't see where I put it. Oh, here it is. This just kind of shows you, if you know it from MATLAB, this is how it works in Python. If you want to do it in Julia, that's how Julia does it. So it's just a conversion sheet. It's just a quickie little something that somebody put out on the internet. At any rate, back onto this, I create a sinusoid, and then I go ahead and plot it, put some labels on it, and then I use a function that is in the library of the SIG-SYS module, which is part of Scikit DSP-Com. This will calculate the power spectral density, something we haven't even learned about yet, but I'm just going to create a power spectrum of that signal, and lo and behold, I have it in a mode that calculates the approximate power in watts, assuming a 1 ohm system, in a two-sided spectrum at that. So it's down at minus 6.02 dB, so this value of the spectral line. And there's my waveform. If I shift that frequency up and run the cell again, it's now shifted up to 200 hertz, still down about minus 6.02 dB, and it's all filled in there because there's a lot of cycles in there now. Does this make sense? Then I put labels in here. I've used f-strings again to put in, variables and things like that. There's just an unlimited number of things you can try to do. Here's the pi and the rex, just to plot a picture of them. A little bit more complicated. I also did, you can do widgets. So this, you can move this around if it's going to respond. It doesn't necessarily respond quickly when I'm running the video recording. But down here, relating to problems 5 and 6, I did do a calculation under power and energy. I created a periodic pulse train, because you have that in a homework problem. And then I did a plot of that, if it will go forth, for me right now. I guess I didn't run the right cell. Or something's backed up. No. It got backed up because it's showing a star, but yet it's not full. Don't know for sure what's going on. I'll go to this Merimo sample notebook, which is kind of patterned after this. So here I just created 2 of them, and maybe this works, maybe it doesn't. Yeah. See, the Merimo network notebook has got a little bit lower latency and can do things a little bit nicer while the video is capturing. But what I was going to say that I've got over here in this notebook, and unless I can or cannot run it, I can't right now. Okay, what do you do if it stops responding? You can always restart it. I'm over time right now, but I'm not going to have you turn in on Friday because I didn't get far enough into this area, but I want you to push forward into this. Bring up this notebook. Try to do some of the picture plotting that's in problem 5. It asks you to draw sketches. Try to draw them in the notebook. The calculations for energy and power are done just by hand. You can cross-check your work in the notebook, though. I want you to do that whenever possible, right? Cross-check your work. Do it by hand. Check it in the notebook. Do a side calculation. The last problem, though, is a very interesting one. It involves a pulse train of triangles, and it wants you to calculate the average power. So I changed the problem from the book because the problem in the book is actually very difficult to do. I think it's a mistake that was made, but I will talk about that next Tuesday. But right now, I want to have the homework due next Tuesday, and it will be due after class. Remember, I said if homework is due on a day of a class, it's due at midnight the day of the class. It'll be due like midnight next Tuesday. My guess is you'll probably have a good head start on it, or you'll have them all done. Sound reasonable?
Chapter 2, 4, 5, and 6.
I want you to turn in, okay, I know we're going over right now. I want you to do I want you to do 5 and 6. Plan to turn in 5 and 6.
You have to do 4. 5.
I want you to do I want you to work the other problems. I'll put out the solutions for the whole thing, but the ones I want you to turn in are text 213B and C, and then text 13 2.14B, but you're changing it to be this problem. The problem in the book, the triangles, and I wanted to show you this actually overlap, and they make for a kind of a nasty calculus problem of integrating. You don't believe it right now, but look at it and draw the picture out. The notebook stopped working for me, but it's so easy to make a disaster of a problem. I mean, a lot of work.
Is it these here, or
It's not a drill problem, no.
I'm in the wrong book?
No, you're in the right book. You just go down. It starts at page 100 is where the problems start.
Right here.
Yeah. No, problems right there.
Okay.
Yeah. It's not the drill problems, it's a problem. Yeah. Thanks for your attention. I'll be up in the lab shortly, and if anybody has questions, I'll be up in the lab.